So the description of the developer package is present on our wiki page. You will find in this page all the information that you need to download and use the developer package. All the instructions that we are going to use, all the command that we're going to use, all the operation that we are doing are present and described inside this page. So I suggest you to open this page on your browser, check here when you are with some doubt, or if you want to get more information about the developer package. We will do an activity based on the developer package. We will just build a new image using the developer package. So the first operation that we need to do is to download the developer package from our page. Pay attention to this point. When you open and download the developer package, you will find 4 rows, okay? And I will explain the meaning. The first one is contains the toolchain in the cross compiler if you are using an ARM host PC. If you want to build the developer package on an ARM PC, you need the toolchain in the cross compiler for ARM architecture, and this is the package that you need for this. If the second line, you will find the source code of the low-level components, so the kernel, the U-boot, trusted firmware, and OP. This is what we need. And the third line is the cross compiler and the toolchain for the x86 architecture, like my PC. The last line is the Rust compiler for x86 architecture. We can do this operation together. So let's expand it. Here. Okay, get software. Okay, as I said, the first line is the developer kit for ARM Cortex 64-bit architecture, including a programming language and cross-compiler and toolchain. We are not interested in. The second line contains the source code, code of the low-level component of the DFP. The third line contains the cross-compiler for an x86 architecture. And the last line is the Rust compiler for x86 PC. Let's download the source code here. I need to accept the license. And I want to download also the toolchain for my PC. Okay, now downloading is progress. Okay, let's wait for this stuff. In the end, what we should obtain is in the downloaded folder the SDK and the source code. Moreover, for using this material, we should follow the instruction present in the wiki page that I presented before. But what I want to do in this workshop is to stay tired, is to take advantage of this package. This is just a set of script that we've set up for this workshop that pack together the operation that we need to do for using the developer package. So this stuff is present in our hotspot GitHub. I suggest you to clone this GitHub on your system, and if you want, you can use this script. We are now going to use the unpack script. Later, we will use the make ship and make kernel, the task script that help you to build the kernel and the ship. So let's start. To use the developer package, okay, first of all, we need to set up our environment. To set up the environment, 3 operations are required. Unpack the tar gz archives, install the cross compiler, extract and patch the low level component. Okay, here. Okay, again. Extract and patch the low level firmware sources. For the first operation, we need to enter inside our working folder, use the tar command from the Linux command line to extract the SDK package. We want to extract the source code, and I prefer to extract it in a different folder. So I'm using the dash capital C switch to point to another folder, the previous one. And also I will open an extra terminal because I want to run two operations in parallel. The second operation that we are going to do is to install the toolchain. To install the toolchain, we just need to run the installer script with the administrative permission. The last operation is just the unpack of the source code. As you can see, my script enter inside each folder. So the external device tree, the G nano driver, I will explain what this is, and the Linux, OP, trusted firmware, U-boot, etc. Okay, let's start with this operation together. Okay, so I'm using for doing this my WSL machine, Windows for Linux machine. So I can work from my Windows PC and doing the operation. I will work in my developer folder demo because I prefer to work from here. Okay, in my folder you can find the SDK and the sources. So I want to unpack the first package. So in this way I can unpack the cross compiler. Second operation, I will unpack the source code. Okay, and I want to launch my Terminator shell. Okay, done. Next step, install the cross compiler. Okay, I'm going to use my Terminator. Okay, from here, cd STM32, okay, SDK. The installation will start from here. The installation process we ask for some is not working. Okay, my PC is thinking something. Okay, the installation process we ask for the installation folder. Okay, here. Okay, I can accept the default folder for the installation, and moreover, it will ask here. You will ask also for overwrite the compiler because it is already installed. I will choose yes, and the extraction start. Last step, installing the source code. So let's move this here. Let's open my WSL window. So I need to go back one folder, STM32 MP2, OpenSTLinux sources, architecture 64-bit. I want to copy here my the OpenSTLinux Developer Helper. Here, okay, and I can run the first script, the unpack script. Okay. As you can see, the unpack script enter inside every folder and unpack and fetch the source code. In the end, it will complete the operation. Okay. While these operations are proceeding, we can go through our presentation, because in the end, what we will obtain is the external folder, and I will explain the content of this folder: the Linux folder, the opt, the TFA, and the U-boot. The DC Nano driver is the driver for the GPU. You know that AP2 is the GPU, and this is the kernel driver for the GPU. And the STM32 MP file package is a folder that contains the configuration for the DDR4 memory. So to tune and configure the DDR in this package. But it is not important now for this operation. For sure, it is included in our build, but we will not explore this package. Let's see what is happening with our operation. Okay, this is proceeding. What about this? Proceeding as well. Okay, let's wait. Okay, this is done. Okay, so we can check the content of our folder now. Okay, we have the external device tree, Linux, opt, TFA, and U-boot. Okay, while the installation of the cross compiler is proceeding, we can go ahead with our operation. So the second operation that we need to complete, the second step, is the lead. Okay, we need to build the trusted firmware, the opt, the U-boot, and the Linux kernel, and the device tree as well. As you know, the device tree is associated with TFA, also another device tree associated with the opt, another device tree associated with U-boot, and another with the kernel. Keep in mind that the trusted firmware will result in a single image. When you build the trusted firmware with the associated device tree, you will obtain a single image. While we are packaging together the opt, the U-boot, and the device tree. So opt, U-boot, and the device tree will result in a single image called FIP, Firmware Image Package. The Linux and the associated device tree will be a different image, will be built in a different image. So at the end of the build, we'll find the trusted firmware for the storage, for the defined storage device, the FIP for the defined storage, and the Linux kernel. How to obtain this? Okay, I suggest to use another script, make FIP. Make FIP create the FIP and the trusted firmware. You can find here in the output that it create the FIP and the trusted firmware. Where is here? Yeah, trusted firmware for USB. The script called make kernel create the kernel, the device tree, and the modules for the kernel. Okay, let's see what happened with our installation. Okay, the installation completed. Okay, we've now installed the cross compiler inside this folder, and I want to notify this this line. In the end of the installation, the cross compiler installation process says each time that you wish to use the SDK in a new session, you need to turn the environment setup script. Okay, it's clear. You need to set up the environment for using the cross compiler. And as you can imagine, in each of these scripts, so on the make kernel, in the make FIP, at the beginning, at the top of the script, I source this environment. Okay, now this is complete. Good. Let's go back and do the operation one by one. Yeah. This build lasts about 5 to 10 minutes. I prefer to work in a folder where I've already built all these materials. So I will work from developer package STM32 MPU source, and from here I can launch STM32 MPU make it. These scripts are available on the hotspot GitHub. So you can explore the content of the script. You will find inside the script the usual, it's a mesh script. So you will find inside the script just a set of operations that enter inside each folder and launch the make process. And in the end, as you can see, you obtain the file, and this file are copied inside the build output folder. LH build up folder. Inside the build up folder, you find the FIP inside the folder, the kernel, and the cafe. Okay, I need to. I want to run the build kernel 2 kernel. Okay, the window of the kernel consists in the configuration of the kernel, and this is the process that configures the kernel using the fragment. We are using the fragment for creating the configuration. You can chat by yourself how to use the fragment, or you can see inside the script how to use them. Okay, and in the end, the script create modules, Linux kernel image, and device tree, and the result is in the build folder. Okay, let's explore what inside the build folder. Inside the build folder, we will find the trusted firmware for USB, the trusted firmware for the EMC, the FIP image, the FIP DDR, the FIP USB, the kernel image, the device tree, and the modules, all together in this folder. And how can we use this? Okay, clear. We can use a flash layout file to define how to write our partition. In the top of the flash layout file, we need to set the flash helpers that are the KFA, the FIP DDR, and FIP. And in the second part of the flash layout, we have to set up the partition that we want to run. And this is what we are going to do in the next step. Board update. I have here my board. As you can see, because of the screen. However, you need to trust me that I have here the board. Okay, see. I'm setting the switch of the board to start the flashing. Okay, the board is connected and ready for flashing. Since I am lazy, I will work from Windows, but cp. Okay, I need to copy the build folder. Where is the command? Okay, here. Oh, alas. Build. Okay, I'm copying the build output inside my Windows PC, and I want to run the operation from my Windows PC, but from command line. So I'm not using the Q programmer, just the Q programmer command line. Here, and I can nudge from here the flashing process. Okay, I can follow the operation from the serial console. Yep. Now the flashing of the board processing, as you can see, I'm just injected the FIP USB. Now I'm writing the okay, done. It's done. Very, very fast. As you can see, it's very fast. Now I can start the board. again, changing the script. And okay, why is repression very fast? It's very fast because I'm just printer. Let me. Okay, move this. Okay, what I've done in my flash layout file is to ask no, and to remove this. Okay, so you have here the explanation of the field. I decided to write this partition, so the trusted firmware, the trusted firmware on the partition 2, so at FSBL first stage bootloader A1, first stage bootloader A2, and the FIP. So they updated just three really small partitions. And what happened on my system is that I'm keeping the OpenSTLinux standard distribution, but only three components, are actually two components because cache is duplicated here. Only two components have been updated. And we can check, okay, we can check here. The date, checking the date of the build, we see that it has been built now. And also here, I remember that there were, okay, also here, December 3, okay? So, way you can update what you want just using the correct configuration of the flash layout. P means update. PE means do not update. And I've just updated 3 partition. And that's all. You can customize in this way your system. And this is the lazy way. Another way to customize the system can be use these files, so the result of the distribution, the developer package build, to overwrite the file inside your standard installation. As Emmanuel explained before me, you have a set inside the standard starter package. You have a set of folder. Inside each folder, you have the files that you can use for flashing the board using QProgrammer. You can simply overwrite this file. So the two TFA, the 3 FIP. And after that, you can use QProgrammer for flashing your custom board with the low-level components updated. What we've missed is the kernel. Okay, let me explain this point. The kernel is not in a single partition because the kernel is inside the boot FS partition. The kernel is inside the file system. So you cannot simply write in a raw mode the partition because the kernel is in this folder. Okay, here look at the kernel in this folder. So to overwrite the kernel, you just need to overwrite this image.gz and also the device script that you want to use. So, okay, I hope that this is clear. The kernel can be overwritten only overwriting the file system. Maybe you can insert a USB key and using USB key you can update the kernel. Okay, I think that now you have a more clear idea of how to use the developer package, and we can move to the distribution package. The distribution package, as I said, is a Yocto distribution. It's mainly a Yocto distribution. So you cannot download it from a single file, cannot download a single archive. You need to use the repo tool for downloading the distribution package. So the distribution package is explained in our wiki page. Also, inside this wiki page, you will find all the information that you need to build by yourself the distribution package. And we are following this operation for creating our custom distribution. Okay, the command that you need to have is the repo. and after you have to launch repo init to initialize your repository, repo sync to synchronize your repository. Let's do this operation together. And okay, I dig. Okay, who's better? Sempre inside the OpenSTLinux version 6 distribution package demo. It's just an empty folder. Okay, and from here repo init. Okay, and this initialize the repo. And the second simple command is repo sync. Repo sync dash J8. The dash J8 switcher means run 8 thread in parallel. I have a wide build from here, so I prefer to launch several jobs simultaneously to speed up the process for downloading the repository. So in this moment, only 2 jobs because maybe I'm just downloading. It's not possible to split the job, but in 3 minutes or less. No, I think less because we are 85%. Okay, done. Okay, that's done. In less than 1 minute, we've downloaded all the distribution package, and we are ready to use it. Distribution package is the set of layer, meta layer, from Yocto distribution. And okay, I need to explain. I need to go back a bit. I need to apologize also because I'm going to simplify a lot what a Yocto distribution is. Many of you are expert of Yocto, and I don't want you to be angry, but I need to simplify a bit because maybe someone is not so familiar with the Yocto concept, but it's better to start from come a starting point. So, what is Yocto? We can say that Yocto is based on 3 main principles. The 3 variables, 2 concepts, and 1 tool. The 3 variables are the distro, the machine, and the image. These are 3 main variables that are present in the Yocto build system. We are not exploring the distro. The distro for us is OpenSTLinux Developer. I'm not exploring this concept. You can check inside the Yocto the documentation what the distro is and how to configure it. I would like to concentrate in the machine and image definition. Machine means your board. The machine is a variable that contains that definition for your board. So you can see that in our case, the machine can be the MP13 disco, MP15 disco, MP15 et al. It is just a single file, a single configuration file that contains the information of your board, the hardware information of your board. The image is a file that contains a list of software and packages that you want to install, that you want to be present in your Yocto distribution. So the machine defines the hardware, the image defines the software, the list of packages. You just need to list here all the packages that you want to include in your distribution. To concept the receipt and the overlay. The receipt is like when you are cooking. When you are cooking, you need the instruction, the configuration information, the weight of the ingredient. Okay, the same. The receipt is a file that contains the instruction to build the Yocto image for a single package. The concept of overlay means that you can apply a layer over another layer and overwrite what has been defined in the previous layer. So if you define a variable in a receipt and you use another receipt to overlay the previous one, you will overwrite the value of the variable present in the lowest receipt. Qual tool? BitBake. BitBake is the tool that you can use for process the instruction inside every receipt to produce the image. So BitBake will start over using checking all the overlay, applying them, and after that start the operation describing inside every receipt. Again, okay, consider that this is page has been extracted for our wiki, and this instruction describes the operation that you need to do for setting up the environment. And the operation is to define a distro, OpenSTLinux Western. As I said, it is our distro. You need to define the machine, and you will choose the machine that you want to use, and after source the setup environment. After that, you can just launch the BitBake with the name of the image that you wanted to create, and that's all. So distro, machine, and image. Very simple concept. The machine, where can you find the machine definition? The path is simple. Meta ST, STM32 MP, conf folder machine, and inside the folder machine you will recognize all our board. So MP25 eval, MP25 disco. This does not exist. Okay, MP13 eval, MP15. It will exist in the future, but not now. MP13, MP13 disco. And what's the content of this kind of file? Okay, it is just a description of the hardware of the board. So we have the description of the boot device that can be MMC, FP card, NOR. You will define here if you want to use the external device tree. We will see later what's the external device tree means. And you need to associate the device tree to every single stored. So okay, in this case, we are using the state device tree for describe the image, the SD card, and the NOR device. And okay, the other optional device tree, external device tree. The boot scheme of P, and the architecture, Cortex A35, because you know that MP2 is Cortex A35 based. The image. You can find the image definition inside meta ST, meta ST OpenSTLinux, receipt ST, folder image. Oh, sorry, meta ST, receipt ST image. And inside image, you will find the ST image Western or ST image core. What's the content? The content of an image file is just a list of applications. So the splash screen, the SSH server, the hardware codecs, clip debug, or you can pack together more than one application. So a package group. We call this a package group to reduce the size of the file. Plus some extra variable. For example, this label require distro feature means that you can use this image only in a WLAN system. Image language, US frame, US, etc. The license, and the label. Okay. Consider that you can find the description of all the possible machine always on our wiki page and in the folder machine, and you need to apply this label when you want to set up the environment. And the same for the image. The image is the argument that you use with the BitBake command.